Hello and welcome to another Piper Pod. Today I'm going to look at the science of acid base and really look at what you should know. So the last lesson we looked at the rules and things that will really help you in your practice in identifying acid base problems. This episode is more for interest base. So with this episode, listen, take notes, do your own research as always recommended, and then fine-tune your ways in which you look at acid base. In the event of having a patient in an acute situation, never sacrifice your ego in understanding for the patient's benefit. Always look at what the problem is first, and then when you have time, practice your understanding of acid base. So to get straight into it, let's look at why acid base is so difficult to remember. So the previous lesson that we went through, we looked at the absolute bare bones of acid base understanding. Okay, so we only told you numbers and I didn't tell you anything about the understanding of it. I gave you a series of rules without actually knowing the science behind it. A lot of the times, unless you're doing it regularly, this is why acid base can be difficult to understand. Another reason is a lot of the maths associated with acid base calculations and understanding of what's happening were done in a time before modern technology was available. So there's certain tests that we can do now that sort of alleviate a lot of the old rules associated with acid base, which just creeps in confusion. The thing that you need to be aware is that all acid base machines are different. Okay, so you need to have a look at your machine and have a look at what it can do and what it can't do. Some machines will actually buffer and accommodate for the difference associated with venous blood gas versus arterial blood gas. Okay, others will use something known as base defect as opposed to base excess. Okay, they'll give you a total carbon dioxide measurement or a bicarb measurement. Okay, so just get used to the machine that you have, learn what it can do, and then learn how to manipulate those numbers. Another thing that people need to be aware of is the concept of hydrogen and your actual bicarbonates. So the result of acid-base problems is associated with these two individual ions. Okay, so pH stands for the power of hydrogen. So the more hydrogen you have within your system, the more acidic that system is going to be. The same too, the more bicarbonate you have within the system, which is a negative ion or an anion, then the more alkaline the system is going to be. The problem is that these two are not independent variables. Okay, these are not the causative agents of the acid-base problems. Okay, these are dependent variables. The body has a somewhat unlimited supply of these two ions in which they can call upon in order to balance out the body. Okay, so today we're going to look at what the actual causes of acid-base problems are, and then look deeper into the science and how we can manipulate those two. Okay, so hydrogen and bicarbonates are the causality effect of a problem. They are not the dependent variables. Another thing that we need to be aware of is, like everything in the body, conservation of charge is very important. Now what that means is the body will always try to maintain a neutral charge within itself. So for every cation, there's an anion. For every positive, there is a negative. Okay, the body will work and work in order to maintain that homeostasis and that conservation of charge. Okay, we talked about this before when we looked at the cardiac and we looked at the conductive system. It's the exact same principle. Okay, the Ohm's law of drift, if you remember that, it's the exact same principle when you're dealing with acid base. And it's that principle that will determine whether or not hydrogen, cation, or bicarbonate, okay, an anion, will increase in number and cause your acid-base problems. Okay, so if it's not all about hydrogen and bicarbonates, then what is it all about? Well, looking at it, the independent variables within the body is three there on the side. We have CO2, SIDs, and we have the acids. Now a strong ion is any ion that when put into a solution, it dissolves. Okay, so if you get table salt, which is sodium chloride combined, and you stick it into solution, you'll actually get individual ions of sodium and chloride. Okay, so they are strong ions. Okay, and the other thing that is an independent variable is your weak acid. Okay, and the main weak acid in which we're going to talk about that has the biggest role to play in acid base is albumin. So I'm not going to dwell too much into that just now, because we'll talk about each of them as we go through and how they have a role in the acid base. Okay, so starting right at the top, the one that most people understand, it's pretty easy to get your head around, and that's your CO2. Everybody by now should know that CO2 has a massive role to play in your acid-base balance. Okay, and the reason for that is the CO2 that you breathe in, carbon dioxide you breathe in, it actually binds with the water at the base of the lungs, okay, and becomes carbonic acid. Okay, a little equation there for you: H2O, CO2, H2CO3. H2CO3 is carbonic acid. Now, the problem with carbonic acid, well, not the problem, sorry, the thing you need to understand about carbonic acid is that it is also a weak acid. And weak acids have trouble maintaining themselves when put into a solution. Like the strong ions, a weak acid will dissociate when associated with liquid. Okay, so carbonic acid is a weak acid, so that will be broken down into 2 hydrogen ions, okay, and a carbonate ion as well. So it's easy to see if pH is measured by how much free-flowing hydrogen ions you have, the more CO2 come into the body, the more eventually free-flowing hydrogen ions are going to be produced. Because for every molecule of CO2 that combines with water, it creates carbonic acid, which turns into 2 hydrogen ions. Hydrogen ions level increase, and that's what gives you your acidic environment. Okay, causes your acidosis. Now, the opposite is a little bit more confusing to understand, because obviously once you have less free-flowing hydrogen ions, then you're going to become alkalotic. Okay, because your bicarbonate levels will outweigh your hydrogen levels, which will give you this alkalotic state. Now, the things that we have to keep in our mind is CO2 and carbonic acid are not evil to the body. Okay, they are needed within the body. A certain level of carbonic acid needs to be produced in order to maintain equilibrium. So if that base level of CO2 isn't coming into the body, 35, numbers that we learnt before, if that's not coming in, then what the body needs to maintain equilibrium is not being produced. So if you have less CO2, then you'll have less free-flowing hydrogen ions, and in contrast more bicarbonate ions, which will cause an alkalotic state. Now, what compounds this issue further is, with all these bicarbonate ions, negatively charged ions flowing through the body, is the body will want to try to maintain that charge neutrality that we talked about before. So what it does is it actually removes calcium ions from your extremity, and that's where you get the carpopedal contractions of your hands, and then all of a sudden you're enriched with large double ionized, okay, so dications, which is what calcium is, and that can sometimes throw it the other way, which the body will answer with more bicarbonate as well. Okay, so that is how your CO2 will cause a respiratory alkalotic state. Now, that's pretty well understood. Okay, it's not revolutionary, it's certainly not new. The connection was made a long time ago, and I'm sure it was included in all your studies. What we'll move on to now is something that's a little bit different and a little bit more based purely on that balancing of ions. Okay, and that is, of course, your strong ion difference. So when you're dealing with a strong ion difference, remembering that a strong ion is essentially any ion that will dissolve in a liquid, the main ones we're looking at is your sodium and your chloride, because as you can see in the graph to the right, they represent the largest amount percentage wise of your cations and anions in the body. Okay, so when we're looking at what is a normal sodium and a normal chloride, the textbooks and the lab results will differ. Okay, but for this particular situation, we're not really interested in the normal numbers. What we're interested in is the difference between those numbers. So if we say a normal sodium is around 140 and a normal chloride is around 102, that will give you a difference of 38. And when we get to the equations later on, that's the number that we'll use, which is normal difference of strong ions, which is 38. Now if we do the subtraction, sodium take away chloride, and we get a number less than 38, then what that means is we've either dropped the amount of sodium cations that we have or increased the amount of anions, chloride, that we have. Either way, the difference has reduced, and that will give us a comparatively larger amount of anions. When you have a larger amount of anions, the body needs to respond by donating cations. Now the cation that is readily available is hydrogen. So hydrogen will be added in order to maintain that neutrality and in turn cause a metabolic acidosis. Now the opposite occurs when you have a number greater than 38, because that only occurs if you have comparatively less anions, chloride, or more sodium cations, leaving a comparatively more cation ratio, which the body will respond with bicarbonate, being an anion, in order to counteract and maintain that neutrality. When you have an increased amount of bicarbonates, then you'll have an alkalotic state. Okay, so that is how strong ion difference will cause a lot of your acidosis and alkalosis. Okay, it's actually the most common cause of your metabolic acid-base problems, is this strong ion difference. So if you're not quite getting it at this stage, that's fine, because we'll talk a little bit more about it further and we'll put it into some practical scenarios for you to understand. But we'll move on to the third independent variable, which is your weak acid. Now the main weak acid that plays a role is your albumin. Okay, so first of all I need you to understand and accept that albumin is an acid. If you want, pause it, Google it, ask, is albumin an acid? Okay, I'll come back saying yes it is. Okay, because you need to get on board that it is in fact an acid, because most of the times when we talk about albumin itself, we don't actually think of it as a weak acid. Okay, we think of it as obviously a plasma protein that has a massive role in the transfer of drugs and transfer of vital enzymes throughout the body. It's within the blood a lot, which is why it plays such a big role when we're dealing with acid-base problems. Now, because albumin itself is a weak acid, okay, when its numbers increase, the same sort of thing happens that happened when the chloride numbers increase. We have an increase of anions within the body, and therefore we need to balance that with more hydrogen ions, okay, more cations in order to counteract. Okay, so that's nice and simple. Okay, it's also simple to think because it's a weak acid, you have more in the body, therefore there's going to be more of a problem. Now when you have less, then what you're having is you have less anions, so you have less of the acids, which means you've got more cations. So to fill up the anion side, you produce bicarbonates. Nice and simple. Now the problem with albumin is, one, it's not very readily measured in general lab studies. It's certainly not commonly included in your ABGs or VBGs, which means that the rules have been made many years ago in order to just accept albumin for what it is, okay, and to sort of assume what the albumin state was when dealing with acid base. But we'll talk about that a little bit more as we move into the equations. Okay, what we need to understand at this stage is when we take an albumin level, we are getting a weight over volume. Okay, so it's usually grams per deciliter is the measurements that come in for albumin, but that can change. As soon as you treat the person, add more fluids, give treatment, blow off more CO2, add more CO2, whatever it is, something will change in the body, which means that the albumin levels can change. The reason that it needs to be brought up, something so obvious as that, is albumin is often measured once and then taken as gospel for the rest of the person's stay. Unlike someone's sodium levels, which can be taken daily, someone's gases that can be taken quite regularly, albumin is usually taken and then that number is accepted, even though it itself can readily change as well. Okay, so that's albumin. Okay, our main weak acid that we're talking about. Now there's other weak acids within the body, but albumin is one of those ones that is supposed to be there at high levels as well. Okay, but when we talk about Aon Gap, you'll see the breakdown. The other thing that plays a role in our acid-base equation and our acid-base understanding is lactate. Okay, now lactate is a byproduct of your lactic acid, and when that's broken down you get a lactate molecule and you get a hydrogen molecule as well. Okay, so lactate is considered within the acid groups and it's been used for a lot of time for signs of your sepsis, signs of bad toxicology and things like that. Okay, so when we're looking at our lactate, then anything over 1 is considered not normal, so 0.5 to 1 is your normal lactate level. Anything over 2 is considered high. Okay, you actually have hyperlactemia if it's over 2. Now if it's over 4, you need to see if the patient has an infection. So if you've got signs of an infection with a lactate over 4, then you need to start your early goal-directed therapies, which is your management for septic shock and things like that. If there's no signs of infection, then you can look at other shock states. Okay, you can look at the person having recent seizure activities, liver failure, even your malignancy cancers can sort of cause this lactate to go up. But if all those sort of things fail, then you really need to start looking at your toxicology, because there is a massive list of toxicologies that will cause your lactate to increase. Okay. So I mentioned lactate quickly purely because it will be part of our equation later to sort of answer why a person in particular has an acid base problem. Okay, so I'm giving you the numbers and the explanations up front, so then it will make sense when we move into the equations themselves. Okay, the last concept that you need to be aware of before we start moving into the breakdown is a base deficit, or as what is commonly called a base excess. Now this is found on many different ABG tests that you'll do, and it's often ignored because it's not understood. Okay, people know what the normal range is, -2 to +2, but then they sort of accept that that is it. But the base deficit or the base excess on your blood gas can let you know straight away if you're dealing with a metabolic problem or not. So the way we get a base excess is the machine that's doing your blood gas analysis will recalculate the numbers based on if your CO2 level was normal. So they set the CO2 level to 40 regardless of what it is really, and therefore eliminate the respiratory component, and they see the acid base problem associated with the numbers, and they give you a numerical value that means how much base or acid you need to add to that body or that mix in order to get a pH of 7.4. Okay, so if you have a negative number, it means that you have a deficiency of base. Okay, because you have 6 negative excess of base. I know it's a little bit double negative, a little bit hard to understand, but your base excess means that. So a positive value means you have too much base, which means you need to add acids, 6 of them, in order to get it back down to 0 to 7.4. Okay, if you have a negative value for your base excess, then it means that you need to add base, alkaline substances, in order to get back to 7.4. Now I'm not saying people use this and they have a little concoction of acid and base on the sides that they inject millimoles. This is just a way of saying how far a person has gone either way within their metabolic acidosis or alkalosis. Okay, it's also going to be used later as the starting point for us to try to explain where the acid base problem is coming from. Now, big thing you need to take from this is obviously what the base excess is, but most of the tests out there will give you a base excess. The equations that we use, we work on a base deficit. Okay, so we need to convert the base excess to a base deficit. Now, if you're lucky enough and you have a machine that gives you the base deficit, then you're fine. If you don't, and you're like most other machines out there, so you just need to swap the negative and positive equation. So if it gives you a base excess and you want to make it a base deficit, then essentially change the negative to a positive or the positive to a negative. That's it. And when we do our examples, we'll explain more. Okay, now a base excess is only utilized, as you could imagine, for metabolic problems. Now, before we move into modern times, I'm going to talk about the Aon Gap. Okay, because the Aon Gap is something that I'm sure you all have heard of, and what it's trying to illustrate is the gap of unknown ions. Okay, so we're looking for the unknown area of the anions in which need to be accounted for, if you will. Okay, so the way we get it is we get sodium, because that represents a huge majority of our cations. Now, some Aon gaps will include potassium, therefore getting literally like 95+% of all cations just with those two, and then they'll take away bicarbonate plus chloride. So if you look at the other side, you get the sodium plus or minus potassium, and we take away chloride and your bicarbonate. And then what is left over is that little other symbol, and obviously the acids as well. So what makes up this Aon gap is your lactate that we already talked about. Okay, you can also get keto acids. You can get certain toxicologies that will fill in the anion space. Albumin is a massive contributor to the Aon gap, as well as phosphate and your sulfate. Now, what can cause a change in your anion gap? Okay, the toxins that can cause a change in the anion gap, I'm not going to list because it's massive, but I've mentioned a little mnemonic at the bottom, cat mud piles. If you look that up, you will get a full list of all the things, all the toxins out there that can alter your anion gap. Okay, because it's very, very exhausting list. Okay. Now, when they say what makes up an anion gap, that's essentially the unknown components of an anion gap. When you look at keto acid, okay, you've heard of ketoacidosis. Okay, it's a very common one. Okay, good old ketogenics, basically encouraging it. Okay, but keto acid fills the anion gap. So the keto acid itself is actually an anion, but when it is in such large concentrations, it needs to be balanced with the hydrogen ions, which makes you acidic. Okay, therefore you get that ketoacidosis. Right, that's the best way to explain it. So that's what the Aon gap is looking for. Now, they tell us that a normal Aon gap is between 10 and 12. Now, what you need to understand is this measurement for Aon gap is Henderson-Hassel equations, things like that. It was made before we were able to measure lactate and albumin. And it was made before we understood what the strong ion difference is. So what we're going to move on to is, instead of looking at your anion gap, we're going to look at a new modern equation in which we can really fine-tune what actually is causing this metabolic problem. Okay, because if we have a normal person like you and I, then if we added up our normal albumin, our normal phosphate, our normal sulfate and lactate, then we will get an Aon gap of 10 to 12. That's what it will be made up of. The problem is without being able to measure it, we'll get an anion gap of 10, but we could have a low albumin, which means one of the other ones, like lactate, or even rarer phosphate, is filling up that anion gap, or a toxin is filling up that anion gap, but it's looking normal. So we need to be able to break down that anion gap, that list of unknowns further, in order to really fine tune what the problem is. So the concept to do that is, instead of looking for the anion gap, we're going to look at the strong ion gap. Okay, so the strong ion gap is what we really want to know. That is the true list of unknowns, things that we are not measuring. Because we're already measuring the strong ion difference between the main ones, sodium and chloride. We're measuring albumin and we're measuring lactate. So they are no longer unknowns. Therefore, the anion gap, okay, is a little bit futile. We need to know exactly if there is a problem that we do not know about. Okay, so this equation, once again, is only done if you have a base deficit. So if the base excess is abnormal, then we do this particular equation. If it's a fully respiratory problem, then this doesn't even come into play. Now the equation, I'll write it a bunch of times as we work through it, but we're looking at the base deficit plus the strong ion difference. Then we're looking at albumin equation. Now the 2.5 times normal albumin take away body albumin is essentially a way so it can balance with the base deficit equation. Okay, that's where the 2.5 has come from. So for every 1 gram per deciliter of albumin, it will have a 2.5 change within the base deficit, positive or negative. If you need to look it up, you'll realize that I did not make this equation up. Realize this is a set equation that is out there, made by incredibly intelligent people. Okay, I'm just parroting their work. Okay, so that's where it comes from. From there, once we get that side of the house, we take away lactate, and then what is left is a numerical value that tells us that we either need to investigate further to see if it's a toxin, a keto problem, okay, something else that is not accounted for, or if we don't need to worry. So if our N value gets between 0 and 2, now technically you can get -2 to 2, the same as your normal base excess. Okay, if it's between those levels, then it's normal. If it's over 2, then it means you have an unexplained metabolic acidosis to some description. Now if it's less than 2, believe it or not, that one there is usually associated with your cation differences. Okay, so if it's if it's a negative sig value, then you're dealing with your hypocalcemia, magnesia, kalemia, maybe some sort of special poisonings like lithium or bromide or something like that, some other cation positively charged toxin. So it's not common to get a negative sig in the human body without knowing about it first, just by doing a simple chemical screen. Okay, so let's work through a particular equation so you understand what this strong ion gap equation is. Okay, so what we need for starters is we need our values. So we need a base excess, we need sodium chloride, we need lactate, and obviously with those we have our general VBG or ABG as well. Now these can be gotten from your iStat itself. If you have a CG4 and an EC8 cartridge, then you'll get all the values you need minus your albumin. Fortunately, your albumin needs to be taken in a lab. It sort of can't be taken in the bush. So just keep that in the back of your mind. So from there, we get our values, okay, as a way to translate what is down. So this person has a acidic problem, in case you didn't pick it up from the base excess. So they have a base excess of -15, which means they have a base deficit of +15. There's our first number, 15. The next number, 140 for sodium, 115 for chloride, 5.2 albumin, and a lactate of 0.5. Okay, so those numbers are normal except for the chloride. The chloride is raised, in case you're wondering. From there, we break it into the equation. So we start with 15, and then we plus our sig So 140 minus 115 is 25. 25 minus 38 is negative 13. So if we go 15 plus negative 13, it equals 2. Which means at this stage, after the first step, we have 2 unexplained acids going on. So then we look at the albumin, and we get a normal value of 5.2. That's good. So 2.5 times 4.2 minus 5.2 is 2.5 times negative 1, which gives us negative 2.5, which leaves us a negative 0.05 base excess, or Aon Gap. And then we minus our lactate of 0.5, which gives us a negative 1. Okay, so what that translates to is one, it's not really a problem that we need to delve into too much because it's been answered. They still have an acidotic problem, but they have what's known as a strong ion difference acidotic problem, meaning there is no hidden acids that we haven't accounted for. That's the big advantage. So what does it mean for you? Does it mean after this presentation you're going to go out and you're going to hold on to patients until you figure out the exact number? Okay, do the full equation, maybe start looking at chronic compensation, things like that. Maybe look at the CO2 and chloride differences, which is things that you can look into. But it's not for that, okay? Because from here we can go further. Okay, we can start looking at chronic conditions and the way that they adapt to CO2. We can look at things like the osmolar gap as well in order to get a better understanding of what is really causing this positive negative problem. But essentially what you need to get out of this particular presentation is do your 6 steps. Okay, your 6 steps will help you a lot and will give you an accurate diagnosis. From there, introduce the base excess. Okay, and start looking at the SID, because that is a common problem in the medical world, is where the chloride levels are just comparatively too high and someone gets acidotic from it. Okay, so start looking at the base excess, realizing that that means that it's a metabolic problem. Look at your strong ions, see if they relate to your acid-base problem, and then for your interest, you can start looking at the Sig-ion gap. Okay, but don't do it at the expense of a patient your first couple of times. Realize that it's a thing, realize that albumin plays a big role, okay, and just try to remember that things like Aon gaps can be misleading when you're dealing with patients with particular problems. Okay, our technology has evolved further than the Aon Gap, so we can start using words like the strong ion gap in our terminology in order to bridge the gap of understanding. Okay, I hope you enjoyed the science behind acid base, and until next time, take care.